probably going to be a little bit of a review. Remind me, who here has had like background in like correlation regression types of analyses before, like at their coursework, right? They sort of touched on it. Okay, this is going to be kind of the main focus outside of some of the repeat measure stuff that we're going to do at the front end is looking at correlational stuff in a general linear model. This is going to be kind of the basis for a lot of more advanced types of analyses that you're going to do. You have a strong command of general linear model, basic principles, assumptions, things like HLMs and SEMs and some of these higher order types of more complicated models. You're going to be able to pull onto those much more quickly. They're going to make more sense. So we're going to focus on a lot of the fundamentals, get you guys strong there, and then later on, if you want to go through, take additional courses and things like that, this should help you out moving forward. Okay, so let's review where we kicked off last semester. Independent sample t-test, right? Remember here what we're doing is we're trying to use this as analyses to determine reliable differences between two population means, okay? So John, when I'm saying population, what am I talking about population means with these mean-based tests?
So it's generalizing the entire
Exactly, right? We're not interested in samples. Sample is a means to an end, right? I don't need a statistical test to tell me whether or not the score in sample 1 is different than sample 2. I can look at them and see if they're the same number. If they're not, they're different, right? What we're interested in doing with these analyses is drawing some inferences about sort of these broader populations. These might be naturally existing populations. This might be men and women, right? Or it could be populations that we've artificially designed, right? Amelia is running this study where one sample gets one version of manipulation and another sample gets another version of manipulation. Population we're talking about is the hypothetical all people who would be exposed to this manipulation versus that manipulation. Those populations didn't exist until you created them. But the idea is if we were to give all people in the universe this and all people in the universe this, would we see differences here, right? And so this is important, and I want you guys to keep this in mind. I think we lose sight of this when we're running our analyses a lot of the times. We don't care about the sample. The sample is a means to try and infer something about the larger population, right? And so if our analyses are only going to be as good as our sample, right? We can only generalize our results to whatever population we actually drew from. And so this starts to become important when we're evaluating our own research, other people's research, things along those lines. So independent sample t-test, we're comparing mean to two unknown populations. We can't get the population, so we get samples. And so we draw sample A from population A, sample B from population B, run our independent sample t-test, and see do these samples differ by more than we would expect due to just random chance if both of these populations are coming from the same actual distribution, right? Because this is, we're saying mean 1 minus mean 2 equals 0, right? That's saying that each one of these populations, they both come from this distribution, right? We might call them different things, but at the end of the day, the distribution of scores are the same, right? Now, we're not expecting these samples to be exactly the same all the time, but what we're looking with this test is seeing, assuming that these two samples are coming from a population with equal mean, are these scores far enough apart, more different than we would expect just under just random sampling variation and things along those lines, okay? Remember this? Anybody have any questions about this? You guys worked with the t-test for half a semester, so I'm pretty sure. Feel comfortable with this? Cool. All right. We also covered our paired sample t-test. Okay. Our hypotheses here are null hypotheses being that the population of different scores is equal to 0. Our alternative hypothesis is the population of different scores is some non-zero value. And Lenny, tell us what we're doing here with this paired sample test. How is it different than our independent sample test?
Because we're looking at the same sample twice.
Yeah, right. This is our repeated measure design, okay? We're not looking at population A and population B. We're looking at the same population under two different conditions, right? Or over two different time periods or something along those lines, right? And so remember that for our paired sample test, our most simple repeated measures analyses, Laura, what is our outcome working with this paired sample test? The difference score, right? So in SPSS, we calculate measures at scores at time 1. When we calculate scores at time 2, the scores at time 1 and time 2 really make a difference? No. All that's going on is we're creating a different score, and this is what we're looking at, right? Our null hypothesis is that in the population, the difference in scores at time 1 and time 2 is equal to 0, right? Sometimes a little bit above, sometimes a little bit below, but on average, there's no change, right? What we're looking at with our alternate hypotheses is we're saying that these different scores that we're getting from this sample exceed what we would expect just due to random chance if, again, the mean of the different scores in the population is actually 0, okay? So again, question we're really asking here is, do the different scores across multiple assessments deviate sufficiently from 0 to conclude some non-zero difference in the population, right? So I've got say a treatment outcome study, right? We start here and we start here, and we say, oh, we see a decrease in symptoms of 5 points. Is that statistically meaningful? I don't know. Depends on a lot of stuff, right? Depending on variability and things like that, that 5 might just be random noise, right? In this sample, it's 5 points down. Next sample might be 5 points up. Who knows, right? In the actual population, there is no difference. We're just getting random variation. What we want to know with our statistical test is whether or not this observed difference that we're seeing is exceeding what we would expect just due to random variation. Okay? And what's the main factor that helps us reduce that expected random variation? What can we do to our studies to decrease the amount of just random variability that we would expect in our data? What do you think, Nick? Larger samples, right? If I've got a huge sample, right, the amount of deviation that I would expect from sample to sample is going to be much smaller than if I have sample sizes of 10 or 20 or something like that. What do we call that? Expected difference across from sample to sample. Yeah, what is it? Our standard error, right? And this is what our whole foundation of statistical stuff is, differential statistics is based on, right? Is the difference we're seeing sufficiently exceed what we would expect just from random sampling variation, which ends up functionally being a question of replicability, right? So I've found this difference. Am I going to find something similar to that same difference each time I run this analysis with different replications? Those are the types of results that we would hope to more often see be statistically significant, as opposed to just a one-off study that found some wacky result that then we cite for 40 years, but no one can ever replicate it again because it's just random variation in small samples. Okay. All right. Questions about paired sample tests? Cool. Then we'll finish up with ANOVA stuff, right? ANOVA stuff is a little bit different because what we're doing with ANOVA, remember, is we're extending out beyond just 2 samples, right? We talked about our between factors, our one-way ANOVA. In this example, we've got 1, 2, 3 different populations that we're interested in testing on some outcome. Does population 1 differ from population 2 and differ from population 3? Okay, and someone to remind me, what are we using as our metric of determining differences within the context of an ANOVA design? Can we just calculate differences in an ANOVA? And why not?
Multiple groups?
Yeah, I don't know what that difference score is going to look like, right? There's 1, 2, 3 different ways that I can calculate differences. I don't know. It's hard for me to make some sense out of that. So what, with our ANOVA designs, what's our metric of determining differences across these groups?
Could be the blank comparison.
Okay,
Or
what-
you mean the statistics though?
Well, we can run some planned comparisons, but for our ANOVA design, if we just want to see if there's differences in there, what's our metric of differences? What do we use? What do we calculate to determine whether or not we're seeing differences in these three populations? Yeah, our omnibus F, and what's that omnibus F based on? What's that? Not quite. Someone tell me what ANOVA means. Okay, the variances, right? It's analysis of variance, right? If I'm seeing large differences across these samples, hey, what's my variance, twin group variance going to be here? Is it going to be large or small?
Large.
Large, right? And what does that large variance tell me?
There are bigger differences.
Right. Across these, and it doesn't matter if I have 3 or 4 or 6 or 10, right? If if there's no variability across these, what does that tell me? All the scores are about the same, right? If I calculate the variance, twin group variance, the variance is quite large, it's telling me, I don't know exactly where it's going on, but there are noticeable differences in the means of these different groups, right? And so I can take that twin group variance and divide it by what? Someone remember?
Error.
Okay, yeah, our mean squared error. And what does our mean squared error represent conceptually?
Error in each group.
Yeah, the variability within each group, right? Because if my grouping factor is what's accounting for differences that we're seeing across these groups, then what should everybody, in each group, what should everybody's, if my grouping factor, my independent variable is a perfect predictor of outcome, what should everybody's score within each group be? All the same, right? We should see no variability in here, right? But we're obviously going to see variability within our groups, right? And we're chalking that up to error. Error in this sense accounts for, or represents anything that we're just not accounting for in the model, right? Because if grouping is our only IV here, and we're seeing differences within people in population theory, I don't know why they're different, because they should all be the same, because they're all part of the same group. If they're not, that's something that we're not accounting for within the model. And so what we do is we take the twin group variance, and then we compare that to within group variance. Well, within group variance is our estimate of error, right? How much just fuzz we have in this model. And when we run that ratio, we see a great deal more between group variance than we're seeing within group variance. Kate, what does that tell us? What might we conclude based on that scenario? Yeah, if I'm seeing a lot more variance proportionally across groups than I'm seeing on average within groups, what am I likely to conclude in that scenario?
That there's something going on.
Yeah, that there's something driving that these three populations aren't actually coming from the same distribution of scores. The mean of these populations are actually different because they're coming from different distributions, right? Now, if the amount of twin group variance is about the same as what we would see with the within group variance, then we're saying, well, we're seeing differences. These scores that we're getting aren't exactly the same, but the differences that we're seeing across here is about what we would expect if we were just drawing 3 random samples from the same distribution. We're going to get some fuzz there, and so then we're probably going to fail to reject our null hypothesis and say it doesn't look like, at least based on these data, we can't claim evidence for anything that's actually going on here. Right? So again, with our ANOVA designs, a couple different options, a couple different possibilities. The differences that we're seeing in this example here could be due to just random fluctuation, right? It could be just random differences, right? Particularly if we've got a lot of variability within these groups. We've got anywhere from like a max and 8-point difference. Maybe that's a big issue, or maybe it's not, right? It kind of depends on the variability we're seeing within there. Or maybe the differences that we're seeing in our observed scores actually reflect some real difference that we're seeing across these populations, right? The distribution of scores here has a different mean than this score, than this population, and that's when we go through follow-up and say, okay, it looks like we've got something here. We're going to jump in and try to tease out and see where that stuff is going on. Ringing bells, or sort of bringing us back to some of that ANOVA stuff. Okay, cool. So up to this point, we've technically been focusing on, with the exception of factorial ANOVA, primarily on univariate statistics. okay? Univariate statistics, we have one IV, one DV, and we're going through and testing stuff there, okay? Univariate statistics are fantastic. They're great. They serve as the building blocks for a lot of our more elaborate analyses. But what are some problems of univariate statistics? Well, one, it can be kind of cumbersome and inefficient, right? Let's say my question is, what's the relation between gender and college performance? Okay. Well, what do we mean by performance? Performance could be a lot of things, right? Performance, and for my study, I'm interested in performance in terms of course load, class attendance, hours of study a week, college GPA, major GPA, subjective investment in your education, how much you like your classes. These are all part of sort of this construct that I'm, overarching construct I'm calling college performance. How many chi-squares and t-tests is that? That's a lot, right? And then we have problems with compounding error and things along those lines, right? And so if we're stuck with univariate statistics, it's just a lot of tests we're having to crank out, right? And this can be problematic. Another thing, and I would argue this is kind of a bigger issue that we run into, if we're restricting ourselves to univariate statistics, it really limits the types of questions that we can ask, right? So in my field, I can ask, what's the relation between trauma severity and psychological distress? Trauma severity is a continuous measure, distress is a continuous measure. You don't have to be a trauma expert to guess what that relationship probably looks like, right? How many times can we demonstrate that before no one starts to care about that because we've already established it, right? Same thing, do men and women in different levels of post-trauma stress? We can test that. There's only so many t-tests and so many times that we can demonstrate that women, on average, are scoring higher levels of trauma-related distress than men. Before that starts to get boring, and then we have no place else to go, right? Is there an association between social support severity and post-traumatic distress? Yes. We're kind of limited, right? And so like, okay, we've kind of resolved that issue. What would be nice and interesting, we start to ask more complex and more interesting questions, but this is hard to do if we're restricting our analyses to certain univariate statistics. So our solution is going to be multivariate statistics. This is where we can start going through and starting to model on. Anybody think of any type of psychological construct or process that's determined by one factor? I don't know. I think it's a safe bet to say that there's nothing out there that anybody is studying that's determined on only one thing, right? And so if we have multiple determinants of behavior, we need to start having statistical analyses that start to get at some of that additional complexity. This is where multivariate statistics start to come in. Multivariate statistics, this is a broad collection of different types of analyses fall under this multivariate umbrella. And there's different versions of multivariate statistics depending on, people will refer to this in different, people start grouping analyses in different types of ways. For the purposes of this class, we're talking about multivariate statistics as anything that involves more than one independent variable and or more than one dependent variable, okay? What we can do with our multivariate statistics starts allowing us to start including multiple predictors, multiple outcomes, right? We can start to look at the relative contribution or the unique effects of a number of different predictors on some outcome, as opposed to looking at each one of those individual predictors on their own model. From a practical standpoint, this is nice because we can start to capitalize on associations between sets of outcomes, right? We can start to increase our power by including designs that have multiple outcomes that have some moderate correlation. If they're too correlated, that's problematic. If they're not correlated enough, that's problematic. But Kate, does Allison run like MANOVA types of stuff sometimes? You know, I don't know. I was bashing MANOVA one time, and I think Lauren was like, "Hey, we run MANOVAs." But this is one of these things where if I have multiple outcomes, right, and I have some proven factor, there are situations under which that MANOVA design, that multivariate ANOVA, is going to be a more powerful test than just running a bunch of individual ANOVA models on moderately correlated outcomes. So we get advantage of power, and this, I think this is again the most important. We can start to increase the complexity and the level of how interesting are more elegant studies that probably do a better job of actually mapping onto sort of how the constructs of interest start to arise, right? So with a multivariate, within a multivariate universe, we can start asking things like, what factors change the relation between trauma and exposure to stress? So I know that trauma exposure and stress, those are related. I know that. What types of things start to change that nature of that relationship? What kind of question am I asking here? That's a moderation question, right? Okay, I know that X and Y are related. Everybody's shown that X and Y are related. That's not news anymore. But what might be interesting is starting to ask what types of factors start to change the nature of that relationship, right? Is this the relation forever and for always under all possible circumstances in the universe ever? Probably not. There are probably things that in context that start to change the strength or direction of that relationship. We can't test that in a univariate model, but we can start to do it with moderation analysis and multiple regression, okay? We can start to ask things like what factors might account for the relation between trauma exposure and prolonged distress. We know that most people who are exposed to trauma bounce back. They're going to be fine. Some people don't. It would be nice to know what's going on and determining what the mechanism of action is in here between trauma and prolonged distress. What type of question are we asking here? It's a mediation question, right? What's the intervening variable? X and Y are related, but why are they related, right? Is there some third factor in there that accounts for that relation? If we account for this thing, if we manipulate it, can we get that relationship to go away, show up, things along those lines, right? A more interesting question. We can also start to layer in multiple factors and say, what are the unique contributions of different risk factors for the occurrence of PTSD? What type of analyses we're going to have talking about here? Yeah, there's a regression model, right? I can say, well, we know from a theory-based standpoint that 1, 2, 3, 4, 5, 6 different things are all sort of known to be related, right? But those things are all probably related to one another. They're probably not distinct things. So if we put them all together, do we see that one of these, so what's the unique relation between X and Y, and start to sort of get a better sense and refine our models a little bit, right? So these are all things that are difficult, if not impossible, to do within the context of univariate designs. But as we start to get into our multivariate analyses, we can start to get more elaborate, ask more interesting questions, and do more interesting research. Okay? Questions on this? All right. So, who here sort of has the onset of a panic attack if you're thinking about trying to develop a study and you have access to the data and you have maybe a question to think, oh Jesus, how am I going to look at this? How am I going to analyze this? Yeah, right? It's scary, right? You like all these different types of things. How do I choose what model I'm actually going to use, right? The nice thing about this is you can start to organize these different models all under the umbrella of your generalized linear model, okay? Your GLM, this is a broad statistical model, includes a number of, the majority of types of analyses that you'll probably encounter over the course of your career in different types of research. There are some things that fall outside the GLM, but that just generally ends up doing like some Bayesian types of analyses and things along those lines. So GLM is a nice general framework for most of the types of things and tools we would use. GLM is your basic internal combustion engine of inferential statistics, at least as we use them in our field, right? Your lawnmower and your Ferrari don't have a whole lot in common, but they're basically working on the same internal, so the principles of an internal combustion engine. Your Ferrari's a lot more bells and whistles, right? There's the difference between your t-test and your sort of hierarchical mixture, your sort of hierarchical mixture latent models and sort of that sort of type of thing, right? It's all, this is much more complicated than this. This can do a lot more things than this, but it's all working on the same basic principles, okay? So, as we're going through getting yourself familiar with basic assumptions, characteristics of this GLM, it's going to help you organize your analyses and say, all right, this is what I have, this is what I test. So what analyses am I going to go through and use that to select your models, and then if you're strong on this stuff, it makes it much, much easier to start to acquire sort of higher order types of things, right? So again, I use folks in Ben's lab just because I know you guys are doing a lot of stuff with EMAs and hierarchical models and longitudinal modeling, and it's above my pay grade. Like, you guys are doing some cool stuff in there, right? But you're in a tough spot if you just don't know anything about statistics, and then all of a sudden you're trying to learn something about EMA designs and things like that, right? So understanding the very basics is going to help strengthen that, and then start to evaluate and critically evaluate your own research, other people's stuff here. So some basic assumptions of your GLM. Linearity assumption. It's assuming that pairs of variables within your model holding some type of linear relationship. Okay. These, as the name suggests, a general linear model is working with a linear function. And if we're working with nonlinear stuff, we're doing things in here to sort of create linear relations between our variables so that we can go through and run the analyses that we'd like to. Linearity assumption, we're assuming that any two variables adequately represented by a straight line. If I plot x and I plot y, my assumption with the GLM is assuming that a straight line does a reasonable job of accounting for the relation between those variables. And if we violate that, if x and y don't hold a linear relation, if x and y have some sort of curvilinear association, what ends up happening is my estimates of the relation between x and y start to get smaller, or we miss them altogether, right? So if we're looking at this, we violated a linear assumption with that graph? No, that's nice, right? That's more than husband's age and wife's age. So people tend to pair within reasonable relation with one another. What about this? So I pulled this off of Google. So I guess we got horsepower and drive ratio. If I'm a mechanical engineer, I'm interested in this stuff. Evelyn, is this, how's our linear assumption working here?
It's not so linear.
Well, maybe, right? It's not as tight as that, right? But do you see another function that's going to do a better job than a straight line in accounting for sort of these relations? Yeah, I don't know, right? Sort of this as a predictor of this is less good than this, right? But in general, if I'm going to model these data, some negative relation between these two things is probably, at least if these are the only data I have, linear model is going to be just as good, if not better, than anything else, right? We want to think about added complexity for very little gain, right? I don't necessarily want to create a really complicated model to pick up an extra, like, 1% of variability in my outcome if a line just does a reasonably good job of accounting for things, right? What about this? Education and income. Amelia, are you shaking your head? What are you seeing here?
It almost looks like an exponential increase.
Yeah, we've got a growth curve thing looking at, right? This is, I might wonder, boy, do I need a quadratic function to capture that, right? So we start kind of low and then come up, right? Now, if I'm looking at the age of education and income, can I represent that with a straight line? What do you think, Haley?
I mean, you could try and put a line of best fit through the bottom part, but
Yeah,
it wouldn't
right.
necessarily be accurate.
Well, and so my line of best fit probably does something like this, right? But I'm probably going to underestimate the true strength of the relation between these two variables because it's not exactly linear. Now, I might run a model, and my linear model might do actually a pretty good job, and then if I compare that against a quadratic model or a curvilinear model, with these data, the curvilinear model is probably going to be a better fit. The question starts to become how much better, right? Does the additional complexity added to the model with putting in a quadratic term, does that justify doing that, right? And this is an important question, right? Sometimes people call this overfitting your data, right? For these data right here, this collection of data that I've got, this sample, quadratic looks kind of nice, right? But if I were to collect these data again, I might not see this. This might be just a sample-specific thing, right? And so we start to worry about getting these super complicated models that aren't actually representing what's going on in the population. It's just describing what happens to be going on in this sample, right? So this is one of the things we want to be thinking about. do our statistical models capture sort of behavior in the population, or are we just capitalizing on sample-specific characteristics? And now I've got a really complicated model that I'm losing parsimony and not getting a whole lot on the backside. Now, age and education, or excuse me, education and income, this is probably not an exact linear function. We might want to go through and look at something a little more complicated here, but something to think about. Okay. What about this? Does the linear model work for this? No? Give me a better model that works for that. Not one, right? And so, I mean, I can draw, I mean, it's a flat line. So these are uncorrelated data, and like this is a true just data cloud. There's absolutely, knowing something about X tells me absolutely zero about anything in Y, right? But this starts to be important as we start going through screening, right? We can see data, right? And we see this. Am I concerned about a violation of a linear assumption here? Not necessarily. The line does just as good as anything else in terms of describing this data, right? What we want to be careful of is that we're not trying to say fit a linear function of something that actually sort of looks something like that, right? Because if we've got an actual, a full quadratic going on in there, and these are my actual data points, something like that, right? What's my best line of linear fit there? What is it?
Vertical line.
Well, we can't do a vertical line because that's not how lines go. What is it?
It would be the kind of work
Jeez. Yeah, it's that, right? If I try and fit a linear model to those data, I'm going to say that there's no relation between X and Y. Is that true? No, right? These two variables are related to one another. It's just our linear model isn't capturing that. You're going to get a correlation of 0 there. And if you're not doing a reasonable job of screening your data and knowing what you're looking at, you could just miss that completely, right? And so is another reason why it's important to go through, screen your data, take a look, so just get a good sense for what's going on. You should know, with any project you're running, you should know your data in and out. You should have a decent sense for all combination of bivariate correlations and so what's going on. You know what the graphs look like, can describe those things. These are the types of things that you can start to tease out some interesting stuff in your data that you may not have hypothesized. Which you're like, wow, I had not expected this, but it looks like I've got a strong curvilinear relation in here. Maybe I need to start thinking about what's going on, what's accounting for this. Is this some sort of weird artifact in my study, or is this actually something that isn't being described adequately in our theories or in previous papers or things along those lines? Right? So we get another pitch for spending time on screening and stuff. Okay. Questions about linearity assumption? All right. Other assumption of our GLM is this idea of additivity. Within our most efficient multivariate models, at least in terms of our predictors, we're assuming that anything that we add to the model as a predictor is something that's adding incrementally to sort of something else that we already have in there. So the idea is that, all right, here's our first predictor in our regression model, and it counts for this chunk of stuff. And then, so here's piece of the pie for my variability and so whatever my outcome is, right? And I add in X1, and X1 accounts for this much, right? And then I add in my second predictor, and that accounts for this here. And I add in the third predictor, and it's accounting for this here, right? This is best case scenario. This isn't, because we work in psychology and everything's related to everything, this isn't how anything actually ever turns out, right? But this is going to be an efficient model, right? Every predictor that you add into the model is accounting for some previously unaccounted for variability in my outcome, right? Here's X1, and it's got that. And then I drop in X2, and it's accounting for a whole different proportion of variability that's related to everything up here. Then I throw in X3, and that's getting something that's unique and not, it's not being attributable to X1 or X2, right? In this scenario, what's the correlation between our three predictors here? Yeah, you're right, what is it?
No.
0, right? We have orthogonal, but these are all uncorrelated variables that we're putting in, and these are getting at unique and different components. Now, when we actually do this in psychological science, we might find that our second predictor adds to the first, but there's a lot of overlap, right? Predictor 1 and predictor 2 are accounting for a lot of the same stuff there. Predictor 2 is just accounting for something that's at least a little bit different than predictor 1. Same thing for predictor 3, predictor 4, and so on and so forth. We in psychology are rarely working with models where we have uncorrelated predictors outside of strong experimental work, right? If people are randomized to condition and so on and so forth, then by definition, things are functionally orthogonal to one another. But in the context of correlational research, which is where a lot of us clinical folks fall in, right? I've got 3 different predictors in my outcome, and they're all correlated 0.5 with one another. Hopefully, you know, that they're getting at some aspect of different pieces or parts, but we've got a less efficient model in something like that, where each one of our predictors is adding uniquely onto the next with no additional overlap. Okay? So this is what we're trying for. This is what we hope for. It's not whatever happens. It's a story of applied statistics, but so this is the general sort of conceptual idea behind additivity. Questions about this? All right. So what does GLM look like? Depending on your complexity of your GLM, it can be quite intense. But in its most simpler form, what we have is just a basic, very straightforward linear function. So let's take, for example, psychological symptoms following motor vehicle accident. So my question is, what's the relation of depression to post-trauma symptoms in accident survivors with PTSD? We've got a sample of 208 people. What I'm looking at here, I want to see determine what the relation is between my measure, my depression scores with my PTSD scores. And one way I could take a look at this is with a very, very basic linear model. Okay, this linear model is saying y hat. This is my expected value. Okay, it's not my real value. It's my expected value. What the model suggests that it should be. My expected value is going to be a function of some starting point plus or minus some subsequent adjustment based on the level of my predictor. So if I run these data, my actual linear function here is my expected value is determined by a starting point of 24.8 plus 1 times whatever the level of my predictor variable is. So based on this equation, Leila, what's my expected value of PTSD when my depression is equal to 0? If PTSD is my outcome, depression is my predictor.
0.
Well, when depression is 0, what's my expected value of PTSD?
Using.
Yep, using.
24.
Yeah, how did you find that out? Yeah. Yeah.
So I gave X, which is depression, 0.
Look at that. You're already an expert in regression already. Exactly, right? If my score, and this is why, again, people are like, oh, I don't want to do statistics without equations. I just want to look at p-values. No, they use this and sort of thinking about what this means. Yeah, literally, if my depression score is equal to 0, I plug 0 in here, that goes away. My expected value is 24.8, right? Suggesting that for people with no depression, I'm expecting that people with PTSD following a motor vehicle accident with a depression score of 0, their PTSD scores are going to be 24.8. Okay? Amelia, what if I have a depression score of, or excuse me here, how about this? What's the expected change in PTSD given a 1 unit change in depression? What's that?
1.
Yeah, right. And how did you tell that?
Is it 1 to 0?
Okay.
one X.
Yeah, it's a 1 point. So per unit increase or decrease in my depression score, I'm expecting, based on my, it's kind of weird how this turned out. This is kind of weird to get sort of a coefficient, an unstandardized coefficient of 1 here. But if we go through and plot this out, this is what we see, right? We actually see now, we can't actually, based on this model, if I just show you this, does this tell you anything about the strength of relation between PTSD and depression? Can you glean anything off of just looking at that? Haley's shaking her head, no, why not?
I mean, we don't, I guess we don't know what X or Y is.
Yeah, if I don't have any idea of the scaling of these measures and things like that, I can't take a look at that and tell anything. But if I plot it out, what am I seeing here, Kate?
I mean, it's relative, I mean, it's not perfect, but we see like a relative increase with PTSD and depression.
Yeah, right. We see that these two things correlate with one another, right? As my depression score goes up, I'm expecting my PTSD score to go up. That doesn't mean that depression is causing PTSD. We're just saying that these things correspond with one another, so that on average, if I'm seeing greater increases in depression scores, this tells me something about likely what's happening with PTSD. This is actually a pretty nice linear effect, right? Concerned with violation of our linearity assumption. Straight line does a pretty good job of accounting for this, right? And so what we can tell based on this is in our actual units of our back depression inventory 2 and our CAPS measure that we're using as an interview measure PTSD, we're expecting that based on these data, 1 unit increase in our depression score is going to correspond to, on average, a 1 unit increase in our predicted or expected value of PTSD. Yes?
What is what
B is just your unstandardized coefficient. This is just notation for the linear models, regression, things like that. A, we refer to this as your intercept, right? This is the expected value of your outcome when all your predictors are equal to 0. B is just your unstandardized coefficient. Okay? Unstandardized coefficient is presented in terms of the actual units of your measures. Okay? So if we go through and we draw a line, this is what we get, right? Nice, strong linear relation between these two things. Okay. Questions on this? All right. So that was our unstandardized solution. And our unstandardized solution has a lot of interpretive value in a lot of different contexts. But there are going to be times when a standardized solution is going to be advantageous. Anybody have an idea when we might want to use a standardized solution? When they're on different scales, which is going to be most of the time, right? And what does a standardized solution give us that's nice or advantageous interpretive stuff? Any ideas? What's that?
It comes up with 1-to-1 ratio, or it can't be.
Yeah, you're getting there. It does become a 1-to-1 ratio. What we do with our standardized solutions, functionally, is we take all our x's, convert them to z-scores, take all our y's, convert those to z-scores, and then regress the z of our outcome onto the z of our predictors. And what that does is it puts everything on a unit scale. Right? What's the mean of z-score? 0, right? And so what we end up having is now, instead of BDI units and CAPS units, we have the z-score BDI, the z-score of CAPS, and now this puts everything on a common metric. And if everything's on a common metric, this improves our interpretability in terms of our coefficients, right? Last, in the previous model, I asked Haley, is this a strong relation? She just correctly said, I don't know. You have to know something about it. You'd have to have a pretty intensive knowledge of these measures in order to sort of gauge anything, and still even then it'd be questionable, right? But if we go through and run our standardized solutions, again, standardized solutions are pretty easy. Again, all they're doing is just creating z-scores of all your x's, creating z-scores of all your y's, and then just running the same model with that stuff, right? But what ends up happening is now we're on a common metric, and our regression line is going to go through and make sure it's by definition going to pass through the point where BDI is 0, and CAPS is 0. Okay. So what does this mean functionally? If the line has to cross through where the z-scores of these variables are equal to 0. What does 0 correspond to in a z-score? Yeah. And so a regression line, by definition, will pass through, will intersect through the point at the average of x and the average of y, right? Now, what are the impacts on this model? What happens, right, to my regression model? Remember that A goes away in our standardized solution. Any thoughts on why that A might disappear? Yeah.
Intercepts on 0.
Intercepts always 0, right? What's the value? What's the expected value of x when or excuse me, what's the expected value of y when x is equal to 0? 0, right? I mean, you can plug a 0 plus this in there, but that's just extra thing you have to write down, right? So our intercept drops away because we know that this regression line is always going to pass through the mean of x and the mean of y. In our standardized solution, the mean of x and the mean of y is equal to 0, just reduces that down, okay? And so we're left then in this simple model with our expected value 0.535x, okay? Someone tell me what this means.
For every 1 unit increase in x, there's a 535 increase in y.
Okay.
And x increase.
Yeah. You're halfway there, right? Because you're exactly right. A 1 unit increase in x is corresponding to a 0.535 unit increase in y. What's the catch with this?
It's standard deviation.
Exactly, right? Because what we're doing now is we regress standard deviation of y on the standard deviation of x, right? So what's a unit, 1 unit increase in x correspond to? A standard deviation unit increase in x, right? So if we're looking at our standardized equation, what we're saying, and literally, and sort of this is a literal interpretation that I want you to make over and over and over again, right? Literally, this is saying that for every standard deviation unit increase in BDI is going to correspond to about a half standard deviation increase in our CAPS scores, right? And so now all of a sudden, this is something that starts to make more interpretive sense, right? I know what a standard deviation is, and I know what a half standard deviation is, right? In our unstandardized model, it sounds like if I have a coefficient of 1, it sounds like, oh, it's equal, sort of going up in terms of x and y, right? But we're actually seeing in the standardized model, it's like, no, it was about, for every standard deviation unit increase in x we have a corresponding half standard deviation unit increase in y, all right? Anybody clever, anybody know what this value is? What do you think? You don't know? John, what do you think? Do you know? It's a standardized regression coefficient, but in this model, what is it? What's it equal to? Yes. Were you going to say something?
I was
You going to say effect size? Yeah. This is your correlation. This is a correlation of x and y right here. Okay. In a predictive regression model with one predictor, right, your standardized coefficient is equal to your correlation, right? So if we were to run Pearson correlation in these data, the answer we would get is exactly 5.3 because it's the same thing. This standardized coefficient, again, in a univariate regression where we only have one predictor, your standardized solution, coefficient in your standardized solution is equal to your correlation. Okay? And so my standardized coefficient here represents my expected standard deviation unit change in y given a standard deviation unit of x. This is nice because I know what constitutes large and small correlations, right? And so now, Nick, if I'm looking at this and I say, oh, my standardized coefficient here is 5.35, how strong is that relationship? Moderate. It's actually large, right? This is a strong relationship. If you say the unstandardized coefficient between x and y is 1, I don't know, that could be a massive relation, or it could be anything that's something that's very close to nothing at all, right? But if you tell me standardized coefficient is 0.535, I go, oh, wow, you've got a really strong relationship there. And so standardization can help in terms of sort of communicating strength of relation without sort of having to know everything about the scaling and all those types of things. And so here's our standardized regression. Is this graph look anything different than the unstandardized? No, it's the exact same thing. Doesn't change the nature of the relationship, doesn't change what the data look like. It's identically this. It's the exact same. We're just playing around with the numbers that we're attaching to it. Okay? And so here we see standard deviation of BDI is about 12. Standard deviation of CAPS is about 22.5, right? So if we want to really get in, I want you to be thinking about regression models in this way, right? This standardized regression, we say that it's about 0.5. We're saying for every 12-point increase in BDI scores, we're going to get about an 11-point increase in our CAPS scores, right? And so wanting you to be able to sort of recognize how to work back and forth with these efficiently to sort of be able to make clear interpretation of this. Yeah, so my standardized coefficient is say, let's call it 0.5, right? So we're saying for, this is saying for every unit increase in X, we're getting about a half of a unit increase in Y, right? Well, I know that this is a standardized coefficient, so I'm saying for every standard deviation unit increase in X, we're going to get a half standard deviation unit increase in Y. Well, if I know what the standard deviation of X and Y is, I can say, well, for every 12-point increase in BDI score, I'm going to get about an 11-point increase in my CAPS on average. That's what I'm expecting. Any questions on this? It's kind of sinking in. We're gonna spend a lot of time talking about this. You guys are gonna be experts at making good interpretations, but this starts to become important as you start to get into hierarchical linear modeling, growth curve modeling, and things along those lines. Sort of more complex linear models starts to become important to know what zero means in your equation. So what these coefficients correspond to in order to start making clever interpretations and stuff. So, our bivariate GLM, right? Bivariate generalized linear model. 3 specific forms. What we're talking about here is we're talking about one predictor and one outcome, right? And how do we gauge the relation between our one predictor and our one outcome? Well, it depends on the level of measurement of our variables, okay? And again, when you're trying to figure out, oh, what analyses should I use or what analyses can I use, think about 1, what am I trying to do? And then 2, level of 2, how many IVs do I have? How many DVs do I have? And then 3, what's the level of measurement of those IVs and those DVs? If you know those 3 pieces of information, you're going to hone in on your analyses really, really quickly. That first chapter of Bivariate and Waddell has a nice graph that goes through, and so you can literally follow it, and it'll tell you exactly sort of, well, it will give not exactly, but it'll give you options on how you might analyze a certain set of data based on certain characteristics, and this is what it's all about, right? Now, if we're talking about things in terms of our bivariate GLM, one predictor and one outcome, right? If our X is continuous and our Y is continuous, what can we use to test the relation between a continuous X and a continuous Y? Nick? Correlation, yeah. Pearson correlation, right? It's just a continuous X, continuous Y. It tells me the strength of the relationship. It tells me direction and magnitude of that association. Easy peasy, okay? What now, though, if I have a dichotomous X and a continuous Y? Okay. So my predictor is dichotomous, my outcome is continuous. What are my options in terms of analysis? T-test, absolutely. Also point by serial correlation, right? We'll talk about that. These 2 tests are equivalent. They're the same thing, right? They're testing the exact same thing. The p-value you get for this is going to be identical to the p-value you get to this. They're mathematically equivalent. The only thing that differs is how we're talking about stuff, okay? What about if I have a dichotomous X and a dichotomous Y? What are my options in terms of analyzing these data? You know, Haley?
Chi-square?
Chi-square, yeah. Or a phi coefficient. This is a functional, these 2 are identical tests, right? This is just terming things in terms of a regression or a correlation coefficient. This is just your chi-square test of independence, right? And so these analyses, your biserial correlation, your t-test, your phi coefficient, your chi-square, these are mathematically equivalent. They are no different. They're the exact same test. only difference is that our GLM, as we're thinking about this, talking about things in terms of the relation between X and Y, as opposed to the difference, right? So I could say, what's the mean difference in extroversion across men and women, right? If I'm telling you that, what type of analysis are you thinking about? Yeah, t-test, right? And saying, is this level higher than this level, right? But I could also frame that, I could say, what's the relation between gender and extroversion, right? It's the same thing, right? It's gonna go through and it's gonna test the exact same thing. That's just, the framing things in terms of relations is just a more flexible way to start thinking about things. And so I can run a t-test, or I can run my point by serial correlation, doesn't matter, because I'm gonna get the same result either way. It just determines how I'm going to think about things. Same thing, I can talk about, our X and Y, my dichotomous X, my dichotomous Y, are they independent of one another? What's the relation between X and Y? Different ways of going through and talking about these things in terms of increasing the flexibility of predictions and things along those lines. Okay? And so again, conceptualizing these versions of the GLM in terms of relations, these basic bivariate forms of the GLM are going to form the basis of subsequent and increasingly complex analyses. And so what we can do is we can start to, if I'm talking about, oh, this is the main difference between X and Y because I've got a dichotomous predictor and a continuous outcome. And it's fine to talk about those main differences. We often will, right? The question is a means-based analysis, and sort of means-based question. Say, are these things two things different? Well, that's cool, but now what if we have two X variables? Say we're looking at gender and I don't know, some other dichotomous outcome or something like that, right? Truly dichotomous outcome. Both of those things are in my model. Well, now it's hard to start talking about mean differences because I've got two predictors, and now all of a sudden my mean-based differences or my group level differences start kind of become more complicated to talk about. But what I can do is I can say this is the unique relation of X on Y holding this constant, or this is the unique relation of this on this holding this other thing constant, right? It just starts to increase your ability to talk about these models flexibly if you're thinking about these in terms of relations as opposed to means-based differences, right? So even like our one-way ANOVA, right? I'm looking at the relation between condition 1, 2, and 3 with some outcome, right? Now I can talk about mean differences across these three groups, or I can say, what's the relation of condition with outcome? That's a much easier and quicker way to start talking about that, right, than means-based differences, right? Still fits in this GLM model, right? I just have one predictor, my predictor is condition, I just have three levels to it, right? I can still run that in a regression model. I don't have to sort of rely on means-based analysis. We'll talk about our means-based analyses, our ANOVAs and things like that are all just a special case of regression. You can run those models. I think maybe you brought that up last semester, or sort of far foreshadowing things. But if we're starting with our basic bivariate GLM, what we can do is we can start to expand that to get at increasingly interesting and a little bit more complex questions. So if I want to add in, not just look at the relation of depression with PTSD, but what I want to do now is look at the relation between depression, trait anxiety, and social support with PTSD in survivors of motor vehicle accidents, right? I can do this really easy by just expanding that bivariate GLM into a simple multivariate GLM. How many IVs do I have in this model? Do I indicate? Yeah, I got three independent. I got three predictors and one outcome here, right? And so what I can do is I run this through and say this is a standardized model, as indicated by my Z-scores. I've got my coefficient for depression, coefficient for anxiety, and my coefficient for social support here. Okay. John, which one of these, if these are standardized coefficients, tell me what's going on in terms of the relative association of these individual predictors with my outcome.
Looks like depression is
Yeah, how do you know that? Well, not a higher standard a larger coefficient, you know, right? Are we concerned about the scaling of these variables in this solution? It's all standardized, right? We're all working on this, because I can look at this and I can say, looks like depression is carrying most of the weight. Anxiety and social support look like they're comparable, perhaps. We've got a positive relation here, a negative relation here. But it still looks like in this horse race, depression or my BDI scores are still the heavy hitter with this. I can't make that interpretation in a non-standardized model, just because this could be 0.05 and this could be 100, and this is a far stronger correlation or association than that. This is where our standardized solutions start to come in and be helpful here. Okay. Important to note that in our multivariate form, these standardized coefficients are beta weights right here. These no longer correspond to correlations. Okay. Because even if you have conceptually unrelated predictors, that correlation between those predictors is never going to be exactly zero. There's going to be some, just even if it's just sort of random overlap, right? And so what these coefficients are now corresponding to is the mean correlation after we partialed everything out, right? So we can't, because sometimes you'll see people say, oh, you just calculate or interpret standardized coefficients as correlations. Like, nope, those are partial coefficients. You absolutely can't do that. We'll talk about this more, but something to have in your head now as we move forward with stuff. Questions about this? Yeah.
So something like this, multiple regression, you can actually state it uniquely predicts as opposed to the simple regression where it just, like, it predicts, in the simple, it predicts like a 0.45 increase in standard deviation, and this we can say uniquely predicts.
Yeah. I mean, so you here technically, and we will get into technical definitions, right? I would say that after holding trade anxiety and social support constant at the mean, I would expect a standard deviation in unit increase in depression to correspond to 0.45 standard deviation increase in my corresponding outcome, right? Because the idea is that we're holding these constant, right? And so what happened relative to my coefficient here? What happened to my coefficient here? It dropped, right? And anybody have an idea why it dropped? What's that, Kate?
Because you had the other two.
Yeah, and I have the other two things in there. What's going on with these other two factors? Why did that cause this one to drop?
Because if they remove some of the predictable.
Exactly, right? Some of the stuff that depression was predicting in my outcome is also predicted by trait anxiety and social support, and so those got removed, right? And so what we have is a partial coefficient that goes through and adjusts for this other stuff, right? Now, if these three things were all correlated exactly zero with one another, Haley, what would my coefficient be here?
Zero.
If my measures were all uncorrelated with one another, what would my coefficient for depression be?
1.
Yeah. 0.535. It would be the same as it was before in just the basic correlation, right? But never in the world where will all of our predictors, even if we completely randomize to condition and things along those lines, right? We're always going to get some just residual association just because of just random stuff, right? And so we'll talk much more about these to get you comfortable with interpreting this stuff. So a simple multivariate GLM. And so this is where some people will say, well, if you talk about, and if you were to take multivariate statistics in like the statistics department, you wouldn't talk about regression or these types of things in there because generally if I'm in the world of statistics and I'm talking about multivariate analysis, I'm talking about fully multivariate analysis where you have multiple IDs, multiple EVs. But you can talk about, we'll talk about this as a simple multivariate design where you've got multiple predictors, just one outcome here. And so if you have continuous predictors, multiple continuous predictors, and one continuous outcome, we're talking about a regression model, right? If I have a discrete set of predictors and one continuous outcome, we're talking about ANOVA, right? ANOVA, factorial ANOVA, things along those lines, right? So I've got condition 1, I'm looking at differences in outcome across conditions 1, 2, and 3, right? But I've got one continuous outcome. I can analyze this in ANOVA. I can also analyze it in regression if I want to give proper coding. If I've got a mixture of categorical and continuous predictors and just one continuous outcome, talk about an ANCOVA model. If I've got a number of continuous predictors and a categorical outcome, we're talking about discriminant function analyses. If I've got a mixture of continuous and categorical predictors and a categorical outcome, we're talking about a logistic regression model. Okay? If we have sort of mixture of predictors and time is our outcome, time until something happens, we're talking about things like survival analyses. We've got time and a mixture of predictors and some continuous outcome, talking about time series analyses, right? And so it can be difficult to know, so, oh, what am I going to do? But if we start looking at how many X's I have, how many Y's I have, and the level of measurement, that can help you start to determine what type of analysis you're going to be using here. So this is what we might call a simple multivariate, where we're still only working with one outcome, but we've got a lot of sort of mixture of predictors here. Okay. Questions of this one? Okay, but we still have some limitations, okay? So the whole reason we got into this whole multivariate thing was because our bivariate analyses were being too restrictive, right? But we can, to this point, we can still level the same criticisms at our multivariate, our simple multivariate models at this point, continue being cumbersome and inefficient, and still kind of limited in the types of interrelations we can take a look at, right? Again, because what if I have multiple outcome variables, right? I want to know the relation between gender and college performance, but I've got 6 different outcomes there that are part of what I'm referring to as college performance, right? Maybe I've got a number, maybe I'm not just interested in gender, but I'm also interested in major and sort of family structure and things along those lines, right? That's a lot of individual regression models to go through and take a look, right? And so what we have at our availability, they get a little bit crazy, we've got our fully multivariate generalized linear model, okay? In this situation, fully multivariate models, we're going to have multiple IVs, we're going to have multiple DVs, okay? This is just kind of an example, right? So we have basically a linear equation on one side of the equals and another linear equation on the other side of the equals, okay? Things get tricky here. So as we're going from our simple multivariate models into our fully multivariate models, what starts to become complicated is we often need to have not just one equation in order to solve this this system. We need to have a couple of different equations to go through and account for interrelations between these variables. Okay, so I have more than one outcome. Often going to need more than one equation. So I don't just have one regression equation. I'm going to need a system of equations to go through and account for sort of the interrelation of these outcomes in multivariate space. Okay, so think about this in terms of algebra. Layla, this first one here, x plus y equals 24. Can you solve that? No, why not? You don't have enough information to come up with a unique solution for that, right? Basically, I can pick, there's an infinite number of possibilities for x, and then once I choose that, then y is determined, right? But just with an open x and an open y, there's no limit to the number of solutions that we can get to that. But what if in addition to this, then I give you this other equation? Now what? Can you solve that? You can't, right? This is sort of exercising old algebra muscles, right? So if I've got x plus 20, x plus y equals 24, right? And I've got 2x minus y equals -6, right? This I can't solve, but if you give me this, now all of a sudden things start to clarify themselves, right? Remember this, so we go through, this is 18, we got 3x, that cancels out. 3x equals 18, what's x? What? You're close. X equals 6, okay? And if I know x equals 6, what's y? Yeah. Y equals 18, okay? So here, I can't come up with a unique solution to that, right? But as soon as I add in another equation, now all of a sudden I can. Now I can solve this and come up with a solution of best fit. This is the idea behind these multivariate models, and it gets a little bit complicated when we're going through and getting into some of these analyses. And we actually aren't going to get into these fully multivariate models probably at all in this class. And they often don't come up a whole lot in terms of the types of things that we do. But just to give you kind of a sense of what's going on here, for linear components in these fully multivariate analyses, you look to these different equations that you need to solve that solution. Depending on what type of analyses you're using, you'll sometimes call these called characteristic roots. Is a DFA type of terminology. Principal components, this is like an EFA type of thing, right? Basically what this is referring to is a set of equations that help account for the interrelations of these data, okay? And when we're doing these, this is just, I guess at this point, just trivia stuff, there exists as many roots as the smallest number of actual Y variables. So if I've got 5 predictors and 3 outcomes, all in a fully multivariate model, how many characteristic roots do I have? 3. Yeah, that's the smallest of the 2, right? So I have 3 different characteristic roots that could be used to solve this system of equations, but we often find that in many cases, right, and this is so, if I'm running an exploratory factor analysis, and I've got 25 items, how many characteristic roots do I have available to me? 25, right? Is it useful to have a factor solution of 25 items with 25 factors? No, that's not a useful thing, right? And so what we often want to do with these types of analyses is be able to describe the interrelations of your variables with as few factors or as few characteristic roots as possible. And oftentimes, depending on what your data look like, you often don't need the max number of roots you have available to you to go through and solve an equation, right? So let's say, for example, just to kind of help you get a visualization of what this might look like. Let's say that we're looking at the association between a set of predictors and a pair of outcome variables. We've got 2 outcome variables, right? And so how many characteristic roots do we have available to us? 2, right? But let's say that here's self-esteem and here's extroversion in multivariate space. And this is my first equation, right? I've got my first root, and so this, don't worry about the summation thing. This is just saying that this is just saying that this is beta 1 x1 plus beta 2 x2 plus beta 3 x3 beta p xp. Okay, this is just sort of basically a linear model that just is easier to write than sort of lining it out like that. So this is just the summed components of all your predictors and scores, right? And this actually does a nice job of differentiating these 2. We've got self-esteem existing right here on this dimension, extroversion hanging out at this end of the dimension. These 2 are separated by this linear component, right? And so we're good to go, right? We only need 1, we don't need 2 to go through and account for this. But let's say, okay, so I think that's interesting. But now what I want to do is I want to add a third outcome. I want to add social desirability in this mix, right? So what I'm trying to do with this model is differentiate self-esteem, extroversion, and social desirability. Now let's say social desirability ends up popping in right here in multivariate space. Okay. Is my one root still sufficient for differentiating self-esteem, extroversion, and social desirability? Why not, Kate? No, you're exactly right. Keep going.
Well, because you're adding in another one, so you have to add that into the equation as well.
Okay.
And it's going in a different direction.
Okay, it's going in a different direction, right? So if we're thinking about this as sort of one plane, right? Because I've got just one plane that my linear function is accounting for, right? here's where here's where self-esteem exists. Where on this line does extroversion exist? Right here, right? Where does social desirability exist? Right here, right? So I can, with this root, I can distinguish between self-esteem and extroversion. And I can distinguish between self-esteem and social desirability. But can I differentiate social desirability and extroversion? Because they exist in the same spot on this line, right? What I need is I need to incorporate a second root, right? My second root now does a reasonable job. Now my second root differentiates this, right? Because I can differentiate self-esteem and social desirability, and I can differentiate self-esteem and extroversion on my first root, but I can't differentiate social desirability and extroversion indistinguishable based on my first equation. But when I layer in my second root, now this can go through and separate extroversion and social desirability, right? Because they exist on this point in my second root, right? Now, on the second root, are self-esteem and extroversion distinguishable? What do you think, John? No, right? On the second root, self-esteem and extroversion exist in the same spot. But these two roots together do a nice job of differentiating all the possibilities, sort of where these data are existing in multivariate space. Right? And so this is kind of a graphical representation of kind of what's going on with some of these fully multivariate analyses. Again, we're not going to get into them a whole lot in this class just because they don't often come up in psychological research, and these approaches have difficulty. So same thing, like, let's say, so with ANOVA, let's say I go through and I find that, okay, so I'm finding differences. I reject the null hypotheses that these 5 groups are equal to one another, right? That's exciting, but then what happens? I give a significant omnibus test, now what do I have to do? What does my omnibus test tell me in a one-way ANOVA? What do you think, Evelyn? Oh, you know this, what's going on? So one-way ANOVA, I have a significant F test. What does that tell me?
The single one.
What's that? I have a significant F test. What does that tell me about mean differences across my groups?
That there's something there.
That there's something there. What do I have to do to figure out where that something is?
You have to either do post-hoc testing.
Yeah.
Or look at the interactions to see where it applies.
Yeah, there's a lot of follow-up stuff that I can do, right? I can say that these are different, but then I got to go through in there and figure out exactly what they're doing. Same thing with these multivariate designs. Multivariate designs will give you a nice omnibus test, right? Let's say we're running a MANOVA design where I'm looking at like 2 different conditions on different substance use outcomes, right? And these substance use outcomes are all kind of interrelated with one another. It can say, yeah, these 2 groups are different on the combination of days of use, intensity of use, or what other types of things you do it, right? And so in the combination of these outcomes, these 2 groups are different, but then what I need to probably do is then do follow-up tests and figure out on what specific dimensions are these groups different, right? So there's no free lunch. Anytime even with these multivariate designs are kind of cool, and it's a nice way to kind of go through and simplify and sort of get a general signal, is there anything there? But the consequence is that now, so think about all the follow-up tests we had to do with ANOVAs and factorial ANOVAs, now add multiple outcomes. And so we'll start to question the actual utility of some of these designs, right? And sort of preferring maybe a smaller set of clean, more parsimonious questions than to let's throw everything in the bucket and see what turns out. So, all right. Oh, okay. And so let's say standard deviation, social desirability. Instead of falling up here, it falls down here. Do we need that second root? No, that second root's useless, right? So we can just go through, and now even though we have 3 outcomes, we only need 1 root to go through and account for that. It does a sufficient job separating that on its own. So for a fully multivariate GLM, if we have multiple continuous x's, multiple continuous y's, we've got canonical correlation. You know, I don't know that I've ever seen a canonical correlation in any research, but it's something that you can do. If I have a multiple set of discrete or categorical predictors and a number of continuous outcomes, we're talking about an ANOVA, right? If I've got a mixture of discrete and continuous predictors and a number of continuous outcomes, multivariate ANOVA. So we've got, this is what we're going to go through. We got a number of discrete predictors, right? And a continuous observation that's a repeated measure. We've got a repeated measures ANOVA, right? So we've got multiple predictors, multiple outcomes, right? I've got latent predictors and continuous outcomes. I'm talking about factor analysis types of stuff. If I've got a number of categorical continuous outcomes and a number of categorical and continuous predictors, we're talking about structural equation models, path models types of things, right? And so it can get big, right? But if you go through and have a good sense for what's going on, and again, when you're trying to select analyses, know what you're trying to do, know what your IVs are, know what your DVs are, and what the level of measurement is of all those things, and that's going to start directing you what analysis you're going to want to look at and stuff. Okay? Questions? How are we feeling about this? Good? All right. Welcome back. This is for Angelon's cohort, is knowing who P-Man was. Battle guy. I had to assign a documentary to get them doing a mix of stuff. All right. So you guys are going to punch me. Don't shut that off yet. We've got 20 minutes. I want to jump real quickly into our second thing, just to knock a couple of these out of the way. We won't get far because we're going to play a game that will be fun. But just want to get started on sort of basic correlation types of things, sort of roll us in the next lecture. So correlation, right? Pretty straightforward. Correlation is nice, correlation is easy, correlation is easy to interpret, right? But some things to start thinking about, and this is, we'll start to get into some of these distinctions a little bit later on when we get into some regression stuff. Correlation is different than regression at a theoretical kind of basis and on a basis of assumptions. Our correlation measure, or our correlation, this is a measure of association between a random variable x and random variable y. What do we, can anybody tell me what we're talking about? We're talking about a random variable. No, go for it. Okay, not, well, it could be, right? Okay, so we're talking about. Okay, you're getting there. You're getting there. Anybody help her out? Okay. If I've got random variable x, that means I've got a big bin of x values, right? And what I'm going to do is I'm just going to reach in and pull out an x value. I'm going to reach in and pull out an x value. I'm going to reach in and pull out an x value. Most of the stuff that we work with in our correlation models are their random variables, right? Things like height, weight, any type of sort of self-report stuff like that, right? I'm just going to go, I'm going to capture some people, and then I'm going to measure it on them, and the outcomes I get, the scores I get, and the scores I get. This is a random variable, right? And so technically, from a correlation standpoint, if I'm running a correlation, I'm assuming that I have random variable x and random variable y. I pull people in, and sort of the scores I get from them are the scores I get from them, okay? And so we're assuming a bivariate normal assumption of sampling area in both x and y. We're going to talk about what this bivariate assumption, bivariate normal assumption is, okay? Now this is different than regression, okay? From a regression, from a technical standpoint, from sort of the development of regression, regression is a statistical model where we're looking at fixed variable x is used to predict observed values on random variable y. Okay? So we're talking about a fixed variable x. What does that mean? Exactly. Close. What I'm doing is I'm saying I'm going to measure, this is my predictor, and I'm going to systematically go through and make sure I've got 5 at this level, 5 at this level, 5 at this level, 5 at this level. I'm going through and systematically, if it's a fixed variable, I'm going through and making sure that I have adequate representation for all possible levels of this variable that I have. It's not random. I'm not just pulling into it and getting whatever I've got, right? The assumption of a regression is that we're regressing our random variable y on some fixed variable x, where we've gone through and systematically sampled all possible values across the range of that scale. Okay? Now, this isn't how we conduct regression. We have a basic violation in almost all regressions that we ever run, but we'll talk about what additional assumptions that we can layer in to help mitigate the potential violations and the potential consequences of running and looking at regressing random variable y on random variable x. This starts to become important because in regression, technically we have no distributional assumptions of our outcome variable. Your y on a regression model, if you run it by the rules, can be distributed however it wants to be. I don't care, right? Where we start to have troubles with needing to have a nice random distribution of my outcome variable is when I violate that fixed effects assumption. If my predictors are random variables, now I need to have certain distributional things that are going on with my outcome in order to make the regression work. Otherwise, all the coefficients are biased and you're way off base, okay? But you'll sometimes hear people make a distinction between correlation and regression. From a theoretical standpoint, regression, again, we're looking at a fixed effect, a set of fixed effects predictors against a random effects, or excuse me, a random variable y. And so our linear regression, again, assumes that we only have sampling variability in y, right? We have no error. Our predictors are measured without error, technically, in a regression model. Again, we don't do this, but we'll talk about implications when we get into regression stuff. Okay. Properties of our correlation coefficients. Right? If we're getting back to correlation, well, this is easy. Random variable x, random variable y, we're just looking at the association between these two. Our correlations bounded by -1 and 1. Okay. Now our regression coefficients, our standardized regression coefficients are. Standardized regression coefficients can exceed 1. Sometimes that usually means we've got something kind of weird going on in the data. But a regression coefficient, -1 to 1, and this regression coefficient telling us two pieces of information, telling us the magnitude of the association and the direction, depending on the coding, right? Magnitude is invariant. Direction is, so you have to kind of know how things are scaled and things like that. But the sign at the front of your correlation is going to tell you direction, and the correlation itself is going to be the magnitude. This is going to be incredibly important because someone's going to do this. Multiple people, you might all do this. Having you go through and calculate correlations and have you tell me to give me an interpretation of it. Someone's going to say, tell me there's an association between x and y. Why am I not going to be happy with that? I don't know the direction, right? I don't know. Maybe eating a hamburger every day makes me lose weight. I don't know unless you tell me. Same thing with mean. You can't just tell me there's a mean difference, right? You have to tell me the direction and things like that. So make sure that you're tuning that. So oftentimes, we generally assume that people understand what direction the relationship is in. But for the purposes of this class, once I need you to exercise those muscles, make sure that you're specifying things. Okay. So the thing that is fun is what we can do is you work with your ability to guess correlations is online at this sort of link here. We can go through and we can get the regression or the correlation gain. Right? So. All right, guess the correlation, right? Who's excited about this, right? This is I just made your weekend, right? So this hours of guess the correlation, turn it into a drinking game. I don't know. Right? My username. What? How about that? Okay, fine. Okay. Oh boy. All right, what's a correlation? What do we think? 0.7? Higher than that. Is it higher than that? What do you think? gotta help me out.
0.8.
0.8? Okay. Let's see. Oh, wow. That's a Super Mario. Dude, we were real, okay, nice. All right. What about that? 0.6? Try 0.6. Oh, yikes. We lost a heart. All right. Oh, gross. Someone help me out. I know we're responsible. What do you think, Haley?
0.15.
0.15. You think?
No, not anymore. 2?
2?
No, lower? Okay. 1?
I don't. We'll try 0.1. 0.46? Oh, okay. I'm not so good at this game today. All right. Oh, what do we think there? 9? 0.9. Okay. You got life back. Okay. This is looking pretty good, right? 0.5. What do you think, Layla?
I don't want the responsibility.
This is high stakes stuff. We'll say 0.5. Okay, pretty good. Okay. Leave. Was it 0.2?
Oh,
0.02. Ah, that's next to, I don't know. I don't know if I'm, what do you think, Laura? 0.1? Okay. Who said, did someone say 0.2? Can I shot him down?
sure. No, it's a 0.02.
0.02, okay, that's, all right, I don't feel so bad. How was 0.4? 0.45? Okay. Okay. All right. We're flirting with danger here. What do we think? John, you know, give me some help here. Oh, I like it. You're getting specific. This is what I ask people, like interference or levels of like distress during trauma. Like, well, how you 0 to 100? How fearful were you? 87. Like, oh, that's very specific. Right? So this is hours of fun that you can spend on your own, and you're welcome for that. Actually, I have to thank Hell for finding the correlation game. It's really hard. Like, I've gone on streaks and done pretty good, but you know, maybe I'll say a person who can sort of like screenshot the highest score on correlation game will get half a grade increase in some way. Right, you bank, I'm not even going to do problem sets. I'm just going to bank on so getting a high score on the correlation game. So yeah, we'll stop there. We won't get into other stuff, but won't have. So we'll have our first problem set due next